You may have seen my instructables project for a DCC signaling and servo controller on instructables. The software on it has now been upgraded to support multi-aspect signals, and these are signals which are more complicated than a simple red-green signal or a semaphore signal that you might see. And there are a number of different signaling systems in use around the world. JMRI has a number of these already modeled, and we're going to have a look at how we would implement one of these signaling systems using the accessory controller. And this also involves using the Panel Pro application from JMRI as well. If you're considering multi-aspect signaling, you're probably also looking at a higher level of automation for your layout, such as block detection and route setting, and Panel Pro can help with that as well. Okay, we're going to crack on with modelling this Norwegian signal. So it's found in the list here. There's a description of what it is. We're going to go with the two-head model, and that has 6 different signal states as represented by 2 different signal heads, one that sits above the other. We have a red-green that's above a yellow-green. So when we're driving a signal head, we need to figure out how many pins on the Arduino we need. Now there are 4 lamps, so most basic cases you'd use 1 pin for each of the 4 lamps, but that's very inefficient. What you'll find when you look at this signal is that certain arrangements are mutually exclusive. So for example, on the top head red never appears with green, and on the bottom head you have yellow or green alternate flashing but not together, and sometimes neither of them is on. What this means is you can actually reduce the logic to just 2 pins. One pin will drive red or green on the top, and the second pin will drive yellow or green or neither on the bottom. In Panel Pro itself, I'll just bring up the signal masthead, and we'll see the codes set up. I won't go into detail as to how to actually set up the signal at this point, but suffice it to say that there are a number of different codes that will all be sent to address 55 that represent the different signal states, and it's these that we need to program into the accessory decoder. So figuring out the logic on this spreadsheet, we have the various signal states on the left. For example, stop is code 0 and diverging is code 21. I've mapped these into basically the codes that are associated with each pin, and we're going to use pins 5 and 6 on the Arduino, and you'll see, for example, that the stop code is code red, that's 0, that appears, and that will be a logic 1 on that pin. And then the green signal on that head is driven by various codes, which are listed across here. And it will be necessary to program the accessory decoder to recognize all of those codes, at which point it will drive that pin logic low and drive the top green lamp on. Accessory controller is programmed over serial, and the code we need to enter is A for a multi-aspect signal, 5 for pin 5, 55 because that's the DCC address, 0 because we do not want any inversion. Then the first bracketed parameters is the logic high, that's driven by code 0, which is sent to the signal. Then the second set of brackets is the low logic state, which is driven by 21, 8, 9 and 10, and then the last 2 sets of parameters are for flashing high and flashing low states, but there are none of those on pin 5, so those are left empty. Then on pin 6, which drives the lower signal head, again 6, 55 because that's the DCC address, 0 because of no inversion. Then the solid logic high and solid logic lows are both empty brackets because we're not driving them solid, we're just driving the flashing states. So flashing high is codes 8 and 10 for yellow, and flashing low is codes 9 and 10 again. So diverging, because it's got code 10 in both the yellow and green, i.e. logic 1, logic 0, means that it will flash alternately. And this is how it's achieved electrically. So the Arduino provides 5 volts and a ground and 2 pins, pin 5 and pin 6. But we take the 5 volt supply and put that through a 3 volt regulator and generate a 3 volt line that then is used to feed the green LEDs. And the reason for that is that the LEDs are effectively in series. If pin 3 or pin 5 are not driving and are high impedance, then there is in theory a conduction path through the green LED and then back through the red one to ground, or in the case of the lower head, green through yellow to ground. And the reason that they don't both come on is because the forward voltage drop of the green LED plus the red LED is about 4 volts, which is higher than the 3.3 volt supply, and so therefore the LEDs won't conduct. And similarly with the yellow and green combination, those have got 2.2 and 2.1 respectively, so it's about 4.3, which is a higher voltage than the 3.3 supply, so again those can't conduct. Now if the pin is driving actively high or low, then for example if it's high, then current can conduct through the 5K1 resistor and through the red LED to ground. 5 volts is reverse biasing the green LED, so it will not illuminate. Now if the pin voltage drops to 0, then the green LED becomes forward biased and the red LED now has 0 volts across it, so that goes out and the green LED will illuminate. And so that's how it's possible to use a single pin to drive 2 LEDs. And if pin 5 goes high, or rather if it goes tri-state, i.e. it becomes an input, then no current will flow because both those LEDs are in series to 3.3 volts, and that's beyond, it's not sufficient to meet the strike voltage on those LEDs combined, and so they stay off. Now we use 2 different resistors so that we can adjust the brightness of those LEDs independently. So let's look at the system in action. Now over here on the right is a DCC controller that's driven by LocoNet. That's another one of my projects. I won't go into too much detail about it, but suffice it to say that it decodes the instructions from Panel Pro and then puts them onto the track. So it's generating a DCC signal with the DCC control superimposed on that, and that comes down this wire here, which would normally be connected to the track, and then it's picked up by the second wire here, which also would be connected to the track, that's feeding the accessory decoder. And the device here rectifies the track voltage to create 12 volts DC to power the accessory controller, but it also takes the DCC signal off the track as well and feeds that into the accessory controller, where it's decoded by the software, and then that then drives the outputs. The most simple example of which being a servo, and then the more complex example being the multi-aspect signals up here. Okay, in action, now Panel Pro will boot with the signal in an indeterminate state or off, but that can be driven by a script. Typically you would start in the stop mode, and then your automation would drive to different states such as diverging and diverging expect stop, diverging expect clear, and diverging expect diverging. And then finally there's a completely off state. Here's a quick overview about setting up Panel Pro. So if you go into Panel Pro and connect to a device. Now I've got one pre-configured, which is why it's opened, but normally you'd go into Preferences and set up your connection. So the connection I have is running LocoNet over TCP into my homemade device, which happens to sit on this IP address here. So this is all running over the home LAN, and it emulates a DCS Digitrax controller. So Panel Pro will communicate with it using the LocoNet protocol. And a simple example of this is to instruct it to control a turnout. So you can control turnout number 2, and that can be thrown or it can be closed. So it's really just binary states. It's either thrown or closed, and that's the same for very simple signals, which could be red or green, for example. So under the tables menu option, you've got signals, signal masts, and then you can add a new signal mast. And the particular mast we're adding is a Norwegian signal. And that needs to be controlled. We're picking the main 2-lamp one, and we're choosing the mast driver to be DCC, which is important. That's the protocol that's going to go out over the track. And that's going to sit on DCC address 55, but it's also necessary to check this box here that talks about an offset address. And as you can see, this signal has 6 distinct states, and it has a code that's associated with each one, and so that's the code that's transmitted over the track and is picked up by the accessory decoder and is what drives the actual signal lamps. Once it's been added to the table, it's editable via the various buttons on it, but by default the thing will boot with an unknown state, and you typically would initialize it maybe at the stop state. There's all sorts of scripts and automation that's possible inside Panel Pro, and I won't go into that here. There are a lot of tutorials on the internet that take you through this in much more detail. It's a very powerful system, but it can be a bit daunting to learn it. Now a look at the accessory controller itself and how it's programmed over serial. So when it first boots, it tells you its software version and reminds you that you have various commands. Capital A is the command that relates to programming MAS signals. The system boots each pin that's connected to a physical server. It doesn't boot pins that are connected to signal aspects. And typing lowercase x will give you the current dump of how each of the pins is configured. So we have a regular aspect signal, basically red-green, on pin 3, address 88. We have a servo on pin 4, and then we have our MAS signal programmed on pins 5 and 6. And you can see here that they're both sitting on DCC address 5. They've got no inversions. They're currently in the tri-state output mode, so that's information for you to tell you what they're actually currently doing. And you can see how they're programmed. So pin 5 is programmed to respond to code 0, will take it high. Codes 21, 8, 9 and 10 will take it low, and there are no codes associated with flashing it. Its current pin state, because it just booted, is the default 127. And I should mention that any code that is not programmed into any one of these boxes will result in the pin itself just going tri-state high impedance. Now, to actually program it, you would type in the sequence that you want. The terminal emulator has actually remembered the sequence we last typed in for pin 6. So that's 55 for the DCC address, 0 for inversion. It's got no high state or low state as such, but it does have a high flashing state driven by codes 8 and 10, and a low flashing state, which was the green LED, driven by codes 9 and 10. When you hit enter, then if those codes are successfully accepted, then you'll see a statement saying put settings, which means it's been written to EEPROM. And again, you can check by entering X one more time. It is also possible to send commands to these pins from serial rather than having to do it through Panel Pro, and that's useful when you're doing setups. I think an example of that is if we want to send a DCC command to pin 55, to address 55, which is the MAS signal, we'll use a capital D followed by 55, which is the address, and then we would then drive it to a state code that we want. For example, we'll drive it to code 8, and that will say OK. And now if we look at X again, you'll see that the 55 address items are both sitting in state 8, which if we look at this here would be green on the top head and flashing yellow on the bottom head. So again, you could look at the hardware and see what's actually going on and confirm that that is the case. Okay, that's it for today. Thanks for watching, and don't forget to like and subscribe.